Hi there, I'm back here, and let's take a look. Last time, as you remember, we looked at the RLC circuit powered by a generator, powered by an AC source. Okay, and we found that we have the following relation for the RLC source: the current, the voltage, right? That is, we have this type of relationship for the AC source, which can also be rewritten as something like that. There is a phi angle for a phase difference between the current and the voltage in this RLC circuit. Notice that the current also has an Imax current that has a rather interesting relation. The relation is this one that I have written here. Let us analyze this type of equation because it gives rise to what we call the resonance of an RLC circuit, right? First, what is resonance, right? What is resonance? No? Resonance is that when you get the most, resonance is when we get the most amplitude of a given vibration. So that's what it is. The conditions, resonance is a condition, when we get the most amplitude of a given vibration. The resonance that we are talking about here is the resonance of the current in the RLC circuit. So the resonance we are talking about here is the resonance of the current in the circuit. Okay? So again, I'm going to put side by side. I'm going to copy this one right in here and place right here. So we want to maximize this value here to reach the resonance. And there is a way to do that, okay? For a given, let us say for a given resistance value, for a given capacitance value, for a given inductance value, what is the resonance frequency of your circuit? Okay? What is the resonance frequency of your circuit? In other words, what is the frequency value for which you get the largest amplitude of the current? And we are going to do that because there is very important practical consequences for finding this relation, okay? Okay, so this problem of resonance is just a problem of maximizing the current Imax with respect to omega. That's what it is. Okay? Delta Vmax is constant because you adjust that in your power supply. You adjust not in your power supply, in your generator. You have set, let's say, the inductor, the capacitor, the inductance, the capacitance, and the resistance value to a given value. Each one has a fixed value, okay? For a given R, L, and C. What is going to be the resonance frequency of your circuit? What's the frequency? And the resonance frequency is dictated by the omega, right? The resonance frequency dictated by the omega, of your circuit. So the idea here is, so this problem is just a mathematical problem, and then I'm going to tell you what the consequences are. Okay? Mathematically speaking, we must find omega for which Imax is maximized. That's when we have resonance. If we look closely at this equation, okay, you are going to see this guy is constant. This guy is constant. You cannot change this one. You cannot change this one. You cannot. I'm gonna boldface those that that cannot be changed. Okay, you cannot change because it's set by your generator. L is set by your circuit. The capacitor is set also by the element of your circuit, and the resistance is set by your circuit. The resistance value. So what we have to do, we have to find the omega to maximize Imax. And looking very closely at this equation, there is no need to differentiate, okay? There is no need to differentiate to find the maximum of this function. All you have to do to maximize this value here is to ensure that this value here is 0. If this value is not here, if this value is not 0, if this value here is not 0, okay, then it's going to be a positive number because it's squared, and it's going to sum up to another value that is in the denominator, right? So the only way that we can maximize Imax is by making this term here equal to 0. Okay? That's just by analysis. You can do that. You can find that out by differentiating as well. Okay? Making this one equal to 0, then Imax is going to be delta V max divided by R. Okay? If this term is not 0, then the Imax is going to be delta V max divided by a term that's greater than R. Okay? The condition to maximize Imax is the following. Okay, equal to 0. And then this frequency here I'm going to call the resonance frequency. Under this condition, omega becomes the resonance frequency of my circuit. And now you can make it as equality, right? And then just solve for omega resonance. Omega resonance pass to the other side. We are going to square omega. Okay, and the L is going to pass to the other side as well. CL or LC. We're not done yet. Because we still have this situation, and now we come up with the square root. Okay, so the only thing that affects the resonance frequency, notice that the only parameters, right? The only parameters that affect the resonance frequency, you see, are the capacitance and inductance. The resistance played no value on the resonance here. The resistance is there just to dampen the circuit. So if you use this value here for the capacitance and the inductance, you are going to have the maximum current amplitude of your circuit. And that's very important, That has very important practical applications, okay? Let me show you a graph that how it looks like. Here, that's how the graph, that's the type of graph that looks like when you plot the current amplitude Imax versus versus omega d divided by omega. Okay. This graph is just a funny way of plotting the Imax. They could have plotted Imax against omega. Okay, but they decide to plot against omega t versus omega, divided by omega for a very important reason. When omega is equal to omega d, which is the resonance frequency, take a look here. That's the resonance frequency. This ratio is going to be equal to 1, right? Outside this value, what happens to the amplitude of the current? When this ratio is equal to 1, you can see that the amplitude of the current is maximal, right? Outside this value here for the ratio, the current decreases, is smaller. Okay, and why is this important? Okay, this is important because if you have a circuit operating exactly here at this frequency, okay, a radio, for example, a transmitter transmitting electromagnetic signals exactly here at this frequency. Okay, if you have even better, if you have a circuit tuned, one primary circuit tuned to this value and another secondary circuit tuned at this value as well, you're going to have maximum current, you're going to have maximum induction in your circuit. That's the important thing here. Once you tune it off a little bit, once you tune a little bit off of this thing, the current is going to be lower, okay? And then what's the consequence for that? This type of behavior can be used, for instance, in tuning the frequency of your circuit into the frequency of a radio station, for instance, that's transmitting some electromagnetic signals, okay? So suppose that we have n stations transmitting electromagnetic that has very powerful circuits that are producing an induced electromagnetic signal. If you're far away from those stations, you can tune your radio to a specific frequency to pick up just one specific station. Okay. However, if you want to pick up another station, what you have to do? You have to tune your radio again, right? Your circuit again to a different inductor and to a different capacitor to pick up the other frequency. That's the practical application of this type of knowledge, of this type of result. Okay. Notice that they use it here. They plot different graphs for different resistances, right? So resistance equal to 10 ohm, 30 ohm, 100 ohm, and so on. And they all have this peak value on the current. Okay, you may still get interference from the other circuits or radio transmission towers, but the difference in signal is going to be much larger for that one in the resonance point. So that's the important implication of this type of circuit. So let's document here in our notes, right? So if you have two circuits, a primary circuit and a secondary circuit, the primary circuit being powered by a generator, right? And the secondary circuit being induced by the primary, okay, comma, you can maximize the current, the induced current in the secondary circuit by matching the capacitance and inductance of this circuit with the frequency of the generator. So that's the, okay? That's how we do it. Don't forget that this process is a wireless process, right? It's a wireless process. You don't have to have the primary circuit physically connected to the secondary circuit. You don't have to have the primary circuit physically connected to the secondary circuit. All those induced electric fields, they do propagate in space. Remember that? We saw that before, right? The induced electric field is going to exist around the primary circuit in free space. You do not have to have a conductor between the primary and secondary circuits. Okay, that is the very principle of wireless communication. That's the very principle of wireless communication. Okay? Suppose you have a powerful circuit, located 1 mile away from your power circuit. I'll call that the primary one, located 1 mile away from your secondary circuit. The primary circuit this primary circuit has a generator that is driven at a given frequency. Right? If we match the secondary circuit to this frequency, then the current is going to be the largest. Then the current in the circuit, the current induced in the secondary circuit, will be in resonance with the primary one. Okay. Now, suppose that we have two primary circuits driven by generators of two different frequencies. Okay, you go omega 1 and omega 2. So one primary circuit has a frequency omega 1 and the other primary circuit has a frequency omega 2. In principle, the secondary circuit, which we call the receiver, which we also call the receiver of the electric field that's being induced by those two circuits. In principle, the secondary circuit will be induced by both primary circuits, right? Primary circuits. In principle. However, if this secondary circuit is tuned to the resonance frequency of the resonance frequency of one of the primary circuits, say omega 1, right? Say omega 1, comma, then the signal from this primary will be the current induced by this primary circuit will be much larger than the current induced by the other primary circuit. That is the very principle of wireless communication. Okay. That's the very principle of wireless communication. On the other hand, here you go. On the other hand, if you want a current to be induced by the second primary circuit, right? By the second primary circuit, you must adjust the secondary circuit in such a way to be in resonance with the frequency of this other primary circuit, right? Must be in resonance. By being in resonance should be, omega 2. So it should have a capacitance and inductance that's in resonance with the frequency of this other primary circuit, omega 2. And it's possible to do that. Okay? It is possible to create a circuit with adjustable inductance or capacitance. Inductance or capacitance. And that's what your receiver radio is all about. When you are tuning your radio your radio to your favorite radio station, your favorite station, you are actually adjusting the inductance and capacitance. Actually, adjust its inductance and capacitance. Okay, so that's the very principle of wireless communication. Okay, RLC circuits. We use RLC circuits in wireless communication, and it all has to do with Faraday's law of electromagnetic induction. Electromagnetic induction. Okay, so that's the idea for the RLC circuit and its practical applications. Here's a table summarizing what we did for all those circuits. Okay, an AC circuit that just has a resistor, that just have a capacitor, that just have an inductor. The current is in phase with the voltage. The current is out of phase with the voltage for a circuit that has a capacitor. The current leads, right, the voltage. In the case of the inductor, the current lags the voltage. And here are the phase differences. Current is in phase with the voltage. Current leads the voltage. But you can also talk about the other way, right? The voltage is in phase with the current. The voltage lags the current. The voltage leads the current, right? Here's the reactance. And here's the current that I just repeated. We don't need that here. And then we have that other circuit that we discussed as well. That is the RLC circuit, powered by a generator. In both cases, we have the circuit powered by a generator. Here go RLC type circuit. Here go type of circuit. Right? We are going to both face it. Type of circuit in this direction. Here is the generator. It's the same thing, right? With the voltage. We have that repeated here, right? For each element separately, right? For each element separately. But now the current is going to be out of phase with the voltage by an angle phi, given by that relation I showed to you before. The reactance, the net reactance, ends up being this equation. That's the term that tells you how you tune your primary circuit. It's just in terms, I just wrote that in terms of the reactance instead of the omega. Okay? Okay, so we talk about the RLC circuit, which by the way are used by transmitting and receiving radio stations. And now we're going to talk about another type of another important device that's called the transformer. We use that all over the place. We have all those transformers out there converting electricity of one voltage to another voltage, okay? And that's an important device. In addition to a generator, generator is an important device, right? The generator uses Faraday's law. The transformers also uses Faraday's law, as well as the RLC circuit for wireless transmission. So transformers are very efficient devices that can convert AC voltage from one value to another and they have very high efficiencies, around 99%. Okay, so assume that we are transmitting at 1000 volt AC, you know, 1000 volts AC signal, right, through the power lines. And there's a, and there's a reason for transmitting voltage at that high voltage, okay? Because it has less loss along the transmission lines. And now you want to bring this voltage from 1000 volts to 120, okay? We call that stepping down the voltage. However, when we increase the voltage to 2000, we can step up the voltage. It's possible to do that with a transformer. And let's see how it works. Okay, just consider two solenoids, but two solenoids of exactly the same diameter. Okay? And it's possible to create a device like that. Here is an illustration of these two solenoids that I just mentioned to you. Okay? Here you go. This is the primary circuit that has a generator, right? My solenoid is wrapped around a magnetized bar, by the way. Those magnetized bars are very important because now they can concentrate all the magnetic field within this region here. You don't have to have this other solenoid inside or outside this solenoid here. That's just another way of inducing a current or a voltage in the secondary circuit by inserting a metallic magnetized material between those two. Now those two are going to be talking with each other, right? What this guy is going to do? The magnetic field of the primary circuit is going to be concentrated here in the bar, and is going to induce an electric current in the secondary circuit. Okay? Because those two bars have the same diameter and consequently the solenoids here have the same diameter, the magnetic flux in this solenoid is going to be equal to the magnetic flux in this solenoid. Okay, and so let's write that down. That's what I wrote that down in my notes. Okay, the induced voltage in the primary is going to be NP delta d phi p dt. Okay, d phi p dt. But the induced voltage in the secondary circuit is going to be the same, right? The same, but just adjusting the subscript values here. Okay, all I gotta do is d phi s dt. But because the cross-sectional area of both coils are the same, this value that you see here is going to be equal to this other value here. The magnetic field inside the secondary coil is going to be equal to the magnetic field inside the primary coil. And also the cross-sectional area of the secondary coil is going to be equal to the cross-sectional area of the primary coil. That's why we can write this relationship here. Doing that, what happens? Okay, don't forget that I'm going to do a secondary step. Okay, this guy here is going to be Vp divided by Np, right? With a negative sign. With a negative sign. And the other one also is going to be Vs by Ns. So look what happens. Now this negative sign cancels out and we have this relation here. Depending on the number of turns of the primary circuit with respect to the number of turns of the secondary circuit, we can come up with different induced voltages in the secondary circuit, okay? So let's see. Suppose that NP is greater than NS. You have more turns in the primary circuit than in the secondary circuit. Then what does it mean? It means that the voltage in the primary circuit is going to be higher than the voltage in the secondary circuit. And in this case, we have a step-down transformer. The voltage in the secondary is going to be smaller than the voltage in the primary. All the way around, we can come up with the inverse, right? If we control the number of turns in each solenoid, we can have the case of a step-up transformer. But there's more to it. What about the current? We're talking about the voltage. What about the current? Okay. So in order to find out the current, we can come up with that. We can use that expression for the power in a circuit, which is VI. V times I is going to be the power in the circuit. In order to have conservation of energy, the power in the primary must be equal to the power in the secondary. And remember that I told you that conversion of energy from the primary to the secondary is very efficient, very close to 100%. Okay, that's why we can do that. It's not exactly like that all the time. Okay, it can be like a 0.9 instead of a 1 here inside. It can be like a 0.9 or 0.99. But for the sake of this course, for the sake of this discussion, let's consider that there is no losses from the primary to the secondary, right? So here you go, the voltage in the primary times the current in the primary is going to be equal to the voltage in the secondary times the current in the secondary. And then we use this relationship here that we got. Okay? Volt in the primary divided by the voltage in the secondary is current in the secondary divided by the current in the primary. And then look what happens, right? We have a step down in if we have a step down in voltage, we're going to have a step up in the current. Okay? We must have that to have conservation of energy. If the voltage decreases in the secondary from the primary to the secondary, then the current is going to increase. Okay, so we have an example here. Let me erase that. Okay, you can look example. I'm gonna example. So you just have an idea how those devices work in a qualitative fashion. So let's take a look at what we covered in this chapter. Okay. We did LC oscillations, damped oscillations, forced oscillations, okay, of the three simple circuits: resistor, only a capacitor, only an inductor, and then all the three combined. Power in alternating circuit just takes advantage of that equation, power equal to VI, and we finally did the transformer. So we are done with chapter 31 here. Okay, our final chapter is on electromagnetic waves. Okay, let's go take a look here. Maxwell's equations and electromagnetic waves, chapter 32. Okay, chapter 32, Maxwell's equations, equations and electromagnetic waves. We're not going to cover everything. Okay, we're going to cover only 32.1, 32.2, and 32.3. Oh, and oh, wait a minute. We still have electromagnetic waves in 33. Okay, that's not the final chapter. It's the one before the final, right? So we're going to cover only 32 Maxwell's equations. There should be just Maxwell's equations and chapter 33, electromagnetic waves. Electromagnetic waves. This one can be done quickly, and one is closely related to the other. Okay. Let us, 32.1, 32.2, and 32.3. I'm not going to cover the other ones. Displacement current. Okay, so let's take a look. Let us take a look at the equations of electricity and magnetism. So far, right? The equations. Let us look. Right? Let us look at the equations of electricity, at the laws of electricity and magnetism we formulated so far. So the first law is Gauss' law of electricity. Okay, so remember, those you have to memorize for the rest of your lives. Okay, we go this one here. E, right, dot E dot dA is equal to what? Q enclosed divided by epsilon, epsilon naught. That's the first one. The second one I also mentioned here is not going to be EDA, it's going to be BDA. And by the way, it's not difficult to memorize those equations, even though they look so complicated, right? It's a closed surface. And then we have two other integrals. But they are not a surface integral, they are a line integral over the path of this one here. I'm gonna put E dot dA first, but it's not dA, it's E dot dL. Okay, which is the law of electromagnetic induction minus d phi b, right, dt. I'm even going to expand it to rewrite it, right, in terms of double integral. This is no longer a closed surface, it's an open surface. I'm spelling that out to emphasize that this integral here is not a closed surface like in this case here. And then we have the other one, that's Faraday's law. And now this one is the Ampere's law. Okay? Ampere's law, mu naught I enclosed, like that. Call that, well, I have some bad news. Some bad news. the last equation is not correct. It's not correct. It was discovered back in the 1850s that this equation that you see here is incomplete. Okay, it was discovered in the 1800s that the last equation is incomplete. And it was a contribution, this was a discovery attributed to James Clerk Maxwell. What he discovered is that this term here have to have a second term. It had to have a second term. Okay? That's because this equation here seemed to be incomplete if you were to get a circuit and solve it for the case of a capacitor. Okay, think about that. If we take this equation exactly at a loop in between the plates of a capacitor, we wouldn't find any current whatsoever flowing from one plate of the capacitor to another one. Okay? The first hint, let's write it like that. The first hint that this equation was incomplete is that when you solved it for an AC circuit with a capacitor, you would find that there was no physical current flowing from one plate of the capacitor to the other one. Okay? In other words, there was a discontinuity in the current between the plates. Okay, let's see if I can illustrate that for you. Okay, this is nicely illustrated in your book right in here. So suppose that this guy is can be any type in an AC circuit, right? This guy is connected to a generator, and then at a given instant of time you have current flowing from the left to the right. If you were to solve that equation for the plates in between, if you were to draw a loop right in here around in the region between the plates, you would find no physical current whatsoever. Ampere's equation holds very well for this region here of the wire, because you have a physical current flowing here at this loop and another physical current flowing at this loop. But when you put a loop in this very region between the plate of the capacitor, and look here at the loop I'm talking about, the Amperian loop that I'm talking about between the plates, you have no physical current whatsoever. This hinted the scientists that there must have been a missing term in Ampere's law. Okay, and after looking very carefully at this problem, Maxwell finally realized that this missing term have to be another type of current. Let's say an invisible type of current that was flowing between the plates of the capacitor. Okay, so the reasoning went just like that, like the following. Okay. In order to correct for this discrepancy, okay, Maxwell started to think that there must be an invisible current flowing between the plates of the capacitor, and he called this current the displacement current, which is not exactly a physical current, which by the way is not exactly a physical current, which by the way is not exactly a physical current, right? And now we are following the steps of James Clerk Maxwell, okay? And by the way, instead of equal here, I'm gonna put approximately, for sure, not even approximately. I'll leave it equal. It's not even approximately. It's equal only for the case where you have a physical current. This equation is good only for the case that we have a physical current. So he figured out that there must have been a second current here a second type of current that we couldn't figure out, that we couldn't see. Okay? And then, working diligently, he discovered that this displacement current was related to another flux. It was actually related, to the electric flux. Something like that. There is a whole, remember, this thing is a law of physics. He couldn't derive it mathematically. He just had to try one or the other. And I had to think very hard about that too, right? So here you go. We have this force equation that now has to be written in the following way. It has to be written this way. This is Maxwell's correction to Ampere's law. And the displacement current I'm talking about is closely related to the electric field that we have here inside this capacitor. It's actually related to the electric flux. If you multiply the electric flux by that epsilon naught constant, you end up getting a constant that you have to end up getting a parameter that has the units of current. Okay? And now Maxwell's equations reduce to the following. After the discovery, those equations, those 4 equations with Maxwell correction became known as the Maxwell's equation. Okay? I'm going to put this term here, and let's not forget that what we have here now, again, just like before, is going to be the derivative of an integral, but now of the electric field. And again, it's going to be an open surface, just like we got here. Notice what we get. We get lines integral of the respective fields that's related to the derivative of the magnetic flux here and the electric flux here. What is electric here becomes magnetic here on the right side. What's magnetic here on the left side becomes electric here on the right side. This was a major achievement, theoretical achievement, and it has very important consequences, okay? And one of the consequences is the following. If a changing magnetic flux induces an electric field, now this set of equations is also telling us that a changing electric flux also induces a magnetic field. If it goes one way, it has to go the other way as well. Okay? And we can come up with an example, a very good example, very similar to what we saw before for a changing magnetic flux inside a solenoid. A changing magnetic flux inside a solenoid induces an electric field outside. Okay. So what about a changing electric flux inside a capacitor? Is it going to induce a magnetic flux? Okay, we can solve this problem. Okay, magnetic field induced by changing electric field. Parallel plate capacitor, circular plate of radius r is being charged, right? As in figure 32.2.1a. Let's take a look at this figure. Right in here. So we have the capacitor here is connected to an AC source, right? The plates of this capacitor are producing an electric field that changes as time goes by because it becomes positively charged and negatively charged. Okay, so what's happening here? This changing electric field is inducing a magnetic field here inside. That's what's happening. In the same way that the electric field was being induced by a magnetic flux in the solenoid. Okay, so let's solve this problem. This is very neat. It's a very nice problem to solve, and I'm going to formulate this problem in a slightly different way that's formulated in the book. Okay, so what do we have? We have an AC source connected to a circular capacitor of radius A and separation plates D. This capacitor becomes charged and discharged at a rate similar to that of the current, right? So it's going to be Q max sine of omega t. So we have the generator generating a current, in a sinusoidal fashion. So what do we want to do? We want to find the electric field variation inside the capacitor. We're going to find the electric flux inside the capacitor. We're going to find the induced magnetic field inside the capacitor and the induced magnetic field outside the capacitor. Okay? So how do we do it? The electric field inside the capacitor, we already know that sigma is divided by epsilon naught, right? And sigma, which is the charge density, is the net charge divided by the area. The net charge is given by this relation here. And if the capacitor has a circular geometry, its area is going to be pi a squared. Q max sine of omega t divided by epsilon naught pi a squared. That's the electric field. That's the item A that I asked, right? The next step is to find the electric flux inside the capacitor. Okay, the electric flux is going to be given by the E dot dA. We know that the electric field is going to be parallel to the area vector inside the capacitor, so the E dot dA is going to be just E dA. The E is this relation that we found previously. Okay. And we are left with calculating just the area. Everything else here is independent of x and y, right? So we end up getting pi a squared. Pi a squared cancels out with pi a squared. What I want to find the net, here you go. So that's the net electric flux throughout the whole area, right, of the capacitor. Would be better if you find the net electric flux throughout the entire area of the capacitor. if you were to pick up just a small portion of the area of the capacitor, then we were going to have not a pi a square here, but a pi r square. Okay, induced magnetic field inside the capacitor is going to be given by, let's do that together. Okay, so we're going to get this equation here. That's where the real problem starts, right? I'm giving just the final answer, but now I'm going to put the step-by-step here for you. Step-by-step solution. Inside that gap within the capacitor, we have no physical current whatsoever. Consequently, the enclosed current is going to be zero. We have just the displacement current. There's no wire connecting one plate of the capacitor to the other, because if you had this wire, the capacitor would be discharged, right? And it wouldn't behave like an actual capacitor. Inside the capacitor for R less than A, we are left with this term here that we already know how to calculate, right? And by the way, we did calculate it. Let's go for the next step. Here is going to be, oh, don't forget E dot dA becomes EDA first. The electric field is going to be given by this term that you see right in here, Q max. Q max sine omega t, epsilon naught. I'm gonna put outside here, since those are all constants, right? Epsilon naught pi a square. Pi a square. Okay, we can go the next step. This requires to take out the Q max from here. It's a constant. I'm gonna put, oh, no. Okay, Q max is a constant. I'll put it right in here. But also I'm going to start canceling some things, right? Epsilon naught here is going to cancel as well. And this sign can be taken out of the integral because it does not depend on the x and y coordinates. And this area here doesn't depend on t as well. Doesn't depend on t. So what we have here, Q max is a constant, can be taken out. We did that. We cancel epsilon naught with this epsilon naught here. Sine of omega t doesn't depend on x and y, so it can be taken out of the integral. But we still have to differentiate it, right, with respect to time. You don't have to integrate it, but you have to differentiate it. The area doesn't depend on time either. The area depends only on the positions, right, on the x and y coordinates. So we can take it out from the derivative term. And because we are taking the flux only from an area that inside the capacitor, just like that area that you saw before, right in here. This one right in here, see? That's R less than big R, or R less than A, right? Now this area here is not going to be the whole area of your capacitor, but it's going to be just a partial area of your capacitor. pi r squared, and the sine becomes cosine. We have to multiply by omega, and whoa, like that. The procedure is very similar to that procedure that we did to find the induced electric field, okay? Here we are just working on the right side. Oh, the pi cancels out the pi, right? This pi cancels with this other pi. And we completed our line as much as we can. Remember, we calculated only the right side of the equation. Now we have to calculate this left side here. Okay, in the left side we are taking that Amperian loop, right? The B, we're going to choose the loop in the same direction as the magnetic field. Consequently, the B dot L is going to have the same direction. The B will have the same magnitude within that loop, that circular loop, so it can be taken out of the integral. And finally, the dl is going to be the length, the integral of dl is going to be the length of this circular path, the length of the circumference, which is 2 pi r. And the final equation is this one right in here. That's the step-by-step. Okay, what else can we do to simplify? We can cancel this r with the other one. And that's all we can do, right? And then we can finalize our relation here. 2 pi okay. Note that the B field increases linearly within the capacitor, within the area of the capacitor. But it also varies as time goes by. Now we will repeat that for the case in which the magnetic field is positions are greater than the radius of the capacitor, right? Okay. The procedure that we follow is very similar to what we did to the previous problem. I'm going to erase this one here so you can do the step by step. Okay, I'm going to just copy this one and I'm going to show you exactly where is the difference in this magnetic field inside the capacitor. Let's see, D. Find the magnetic field outside the capacitor for R greater. It's not outside the capacitor, it's inside the capacitor, but it's for R greater than A, right? Out the bounds, okay? Outside the bounds of the capacitor. Find the induced magnetic field inside the capacitor for R greater than A. Yeah, it's okay. So now, what do I mean? I mean the region right in here. But it's still within, in that position within the volume of the capacitor, but is outside for R greater than A. This one here, R greater than A. What would be the magnetic field here? From the center to the radius A, the magnetic field increases linearly. But what is going to be for, what's the behavior of the magnetic field in this region for R greater than A, right? We did something again similar for the electric field, right? Okay, so we have the same thing as before. CD, okay, B dot dl, mu naught enclosed is going to be 0. Okay, we have this integral just like before. The only difference now is going to be this integral here, because we have to integrate throughout the entire area of the capacitor. Okay, we are going to have a uniform electric field within that region of the capacitor, but just outside the capacitor the electric field is going to be 0. The uniform electric field is going to be 0. Okay, we have here the electric field. It doesn't change here. What changes is going to be this one. So instead, okay, this one here, the integral, Q max, the derivative is going to become omega cosine of omega t. And we have, and this area is no longer going to be pi r squared, it's going to be pi a squared. Because now we are taking the flux throughout the entire area of the capacitor. Okay, and can we go to the next step? Yeah, we can. The a squared cancel out with the other a squared. Pi gonna be here. The a cancel out. Notice the difference between the field outside the capacitor and inside the capacitor. The result, right? For the field outside the capacitor and inside the capacitor. This r squared, which is going to be a squared, is going to cancel out this one. And now we are left, just like before, with the left side of the integral, okay? Which is exactly the same as we did before. And now, since we have, since we do not have, here you go, we have this relation here. The difference is that on the left side we're going to have r. On the right side we are not going to have r squared. We're not going to have r squared divided by a squared. We're going to have a squared divided by a squared. That's why you don't see the term in there. And now you can finish the problem. Right? There's going to be r here and nothing here. And note, see that the B field decreases with the distance r, just like we had for the E field, for the induced E field induced by the solenoid, right? Notice that the B field induced by the capacitor decreases the distance r, just like we had for the induced E field by the solenoid. Okay, and we are done with this chapter as well, which by the way is chapter 32. Okay.